Hello Math 122. In this video we'll be covering section 5.5, all about the fundamental theorem of calculus. So in previous sections, remember that if we have a function f of x, and this function gives us the rate of change of some quantity, whatever that might be, then we discussed the fact that the definite integral from a to b of that function f of x is going to give us the total change in that quantity from x equals a to x equals b. And ultimately, the point of this video is to formalize this idea a bit more into what's known as the fundamental theorem of calculus. And based on the name, you might guess it is the most important theorem in all of calculus. So, for example, just to review this topic that we've talked about before, say that the function we're looking at is v of t, so that this function gives us the velocity of some object, and s of t is the function that gives the position of that object. Then we said that the change in position from time equals a to time equals b is equal to the integral from a to b of v of t dt. So this is just a particular example of the idea that was in the previous bullet point here. Okay, but an important thing to notice that the change in position could also just be represented as the position at B minus the position at A. So we have a kind of equality that's going on here. We have the change in position from t equals A to t equals B being equal to this definite integral, but this second line tells me that the change in position from t equals A to t equals B is also just equal to the position function at B minus the position function at A. So we end up with this equality down here. S of b minus s of a is equal to the definite integral from a to b of v of t dt. And this is just one particular instance of the fundamental theorem of calculus. So here's the fundamental theorem for you. If we have a function f prime of x, and this function is continuous on an interval from a to b, so I don't think we've talked about continuity too much throughout this course. If you don't understand what this means, that's not really that big of a deal. All of the functions that we're going to be looking at are going to be continuous basically everywhere, so I wouldn't worry about it for now. Then we have this following relationship. Then the integral from a to b of that derivative function f prime of x dx is equal to f of b, so f at the rightmost endpoint, minus f at the leftmost endpoint of the interval. So in words, the definite integral of the derivative of a function gives the total change in the function. And this is an idea that we've seen over and over again throughout this entire chapter. Okay, so this theorem is extremely important, hence the name, the fundamental theorem of calculus, and ultimately it's a way to relate the two main operations that we have in calculus, differentiation and integration. So differentiation is the operation we talked about from chapters 2 through 4, and integration we've talked about throughout chapter 5, and we'll talk about it in chapter 6 as well. And ultimately in section 6.3, we'll learn how to use this fundamental theorem of calculus to evaluate some of the definite integrals that can show up without having to use a calculator like we've been doing so far. So the first example that I want to cover just solidifies some of the ideas that are showing up inside of the statement of the fundamental theorem of calculus. So for this example, we have a train that leaves a city traveling on some straight track, and the distance from the city to the location of the train is given by a function s of t, and the velocity of the train is given by another function v of t. So there are two parts to this question, and the first part asks us to use the function v of t, so the velocity of the train, to calculate the total distance the train has traveled from t equals a to t equals b. And the second part, we're going to do the same thing, but instead of using the velocity function, we'll use the position function that's given to us. And we find out that there's a way to represent the distance that the train has traveled using either of the functions. This is one of the key ideas from the fundamental theorem of calculus. Okay, so first off, we're using the velocity function to find the total distance the train has traveled from t equals a to t equals b. So something that we've talked about before, not even necessarily in this section, is that the total distance that the train has traveled is equal to the area under the velocity curve, which is the same as this definite integral from a to b of v of t dt. So the total distance that the train has traveled is equal to this definite integral, and this gives us the total distance in terms of the velocity function. In the second part, we want to use the position function instead. So we use the position function to find the total distance the train has traveled from t equals a to t equals b. And this time, we have that the total distance that the train has traveled is just going to be equal to the position of the train at the end of the time interval minus the position of the train at the beginning of the time interval. And maybe I'll draw a picture to show what's going on here. So we have, this is our track right here. So this is the train track. And then all the way over at the left, we have time is equal to 0. So this is the city where the train is starting. And let's say that this is time equals A, and this is time equals B over here. So here's the location of the train at time equals A, and we could also write that as S of A, because S of A gives us the position of the train at time equals A, and at time equals B, this dot represents the location of the train at t equals B, which could also be written as S of B. And if we want to find the total distance that the train has traveled between time equals A and time equals B, well, we're just going to look at the distance between these 2 points, which gives us S of B minus S of A. So that's where this expression here is coming from. But notice that now this gives us an expression for the total distance the train has traveled in terms of the position function, as opposed to the velocity function. And we can set these two things equal to one another, which would give us the fundamental theorem of calculus. The next example is our first conceptual application of the fundamental theorem of calculus. So in this case, let this function f of t denote the value of an investment with respect to time in years, so that f prime of t gives the rate of change of the investment value at any time. And suppose that the derivative function f prime of t looks like the following graph. So f prime of t is going to be this blue curve here. And we have two questions related to this. So the first question, when is the value of the investment increasing in value? When is it decreasing? So this is a question that we probably could have answered in chapter 4. So remember that when the derivative function f prime of t is less than 0, we know that the function f of t is decreasing. And we have that when the derivative function is greater than 0, f of t is increasing. And now we just have to go back up to the curve f prime of t and figure out when is f prime of t negative, when is f prime of t positive, and that'll tell us when the investment value is decreasing or increasing. So f of t is going to be decreasing from t equals 0 to t equals 3, because if we look up at f prime of t, that's when f prime of t is going to be negative. And we have f of t is increasing from t equals 3 to t equals 5, because again, looking at the graph of f prime of t, we see that f prime of t is positive from t equals 3 all the way over to t equals 5. Okay, in the second question, this is more related to chapter 5. Does the investment decrease or increase in value over the entirety of the 5 years? So here we're going to use the fundamental theorem of calculus. So we have that the total change in the value of the investment from time equals 0 to time equals 5 is given by the following definite integral. So we have the integral from 0 to 5 of the derivative function dt. And again, this derivative function is given to us, and we can understand this definite integral as the area, where some of the area under the curve is counted negatively, and the area above the curve is counted positively. So, looking at the graph, we have to determine, is this definite integral from 0 to 5 of the derivative function going to be negative or is it going to be positive? Well, if I look at this first area under the curve, and I look at this second area over the curve, remember that the first area is going to be counted negatively, the second area is going to be counted positively when I take the definite integral, and a1 is bigger than a2 here. So maybe I'll write that down here. The first area is going to be bigger than the second area, so this definite integral from 0 to 5 of the derivative function is negative. So the value of the investment is smaller after 5 years than the value when first invested. So here we're using the fact that the total change from t equals 0 to t equals 5 is given by this definite integral of the derivative function, and just looking at the graph we know that this definite integral has to be negative because the area of a1 is bigger than the area of a2, and a1 is counted as negative area and a2 is counted as positive area. So when we take the two and sum them together, we end up getting a negative value. So this tells us the total change is going to be negative, which means that the investment is smaller at the end of those 5 years than the value of the investment when it was first invested. In the last section of this video, we're going to take the fundamental theorem of calculus and apply it to the marginal cost and the cost functions that we've seen before. So remember that the marginal cost function, which we can denote as mc of q, is defined to be the derivative of the cost function c of q. And therefore, by the fundamental theorem of calculus, the total change in the cost from q equals a to q equals b for some a and b is given by the definite integral from a to b of the marginal cost function. And this definite integral from a to b of the marginal cost function c prime is going to be equal to the cost function at the right endpoint minus the cost function at the left endpoint. So this is just an application of the fundamental theorem of calculus to a particular function here. And we can summarize all of these ideas in the following box. So I'll go through it for you. So we let c prime of q denote the marginal cost function, and remember that the cost function at 0 gives us the fixed cost. Then the cost to increase production from q equals a to q equals b is given by either the cost at b minus the cost at a, or the definite integral from a to b of the marginal cost function. We also have that the total variable cost, which is just another way to say the cost without including the fixed cost, or the value of the cost function at 0, to produce q equals b units can be given by the following. So we have the cost at b minus the fixed cost is equal to the integral from 0 to b of c prime of q. So this is just a particular instance of the previous bullet point inside of this box, where we take a to be 0. So if you look up at this equation and you make a equal to 0, then you get this next equation here, and that'll give us the total variable cost. And then finally, the total cost of producing b units is given by c of b, which is equal to the fixed cost, c at 0, plus the total variable cost, so the integral from 0 to b of c prime of q. And again, this equation here can be derived from the previous equation just by taking c of 0 and moving it over to the right-hand side of the equation. But it's important to write this last equation because it allows us to find the cost when we produce a certain number of units just by using the definite integral and the fixed cost together. In this last example, we'll use this new information we have relating the marginal cost and the cost function. So in this case, suppose that the marginal cost is given by C prime of Q is equal to 0.01 times Q. And also assume that the fixed cost is $1,000. Then we want to find the total cost of producing 250 items. So to start off, we know that the total cost is equal to the fixed cost plus the total variable cost. And this is just another way of writing this last equation that showed up in the previous box. Okay, and here we have that the fixed cost is equal to the cost function at 0, which is equal to $1,000. So that's given to us in the problem statement. And the total variable cost is defined to be the integral from 0 to 250 items of the marginal cost function. So we're going from 0 and we're going up to 250 because we're interested in the total cost when we produce 250 items. So now we can say that the total cost is equal to 1,000, so we have our fixed cost, plus the total variable cost, which we just said is the integral from 0 to 250 of C prime of Q dQ, which is equal to 1,000 plus the integral from 0 to 250 of 0.01 times Q dQ. And now we have an expression that's going to give us this total cost to produce 250 items, and we can calculate this definite integral by taking it and plugging it into a calculator. So now over in Desmos, we're going to take that definite integral from 0 to 250 of the function 0.01 times Q dQ, and we get 312.5. So now back in OneNote, we have that the total cost is equal to the fixed cost, which is 1,000, plus the total variable cost, which we just calculated to be 312.5. And so we get a total cost to produce 250 items of $1,312.5. So this would be our final answer. So the key to this example is that we can find the total cost of producing a certain number of items just by knowing the fixed cost, so the value of the cost function at 0, and then an equation that gives us the marginal cost function. And we can do that by using the fundamental theorem of calculus, which is again given inside of this box above. Finally, I want to end the video by giving a little bit of a bird's eye view of what's going on here. So notice that in this section, we have in some sense a way to go from the derivative back to the original function, which is an idea that we wanted to discover all the way back in section 5.1. So roughly, a picture to describe this relationship: if we start with this function f of x, then we can get to the derivative function by this operation of differentiation. So this takes us kind of down to the derivative function in a sense. And all throughout this chapter, in chapter 5, we've been developing the definite integral, and ultimately this definite integral is a way for us to get from this derivative function back up to the original function. So in some sense, this operation of differentiation and the operation of integration are inverse operations, at least roughly. So hopefully this is enough information for you guys to get through section 5.5. As always, email me if you have any questions, and attend the SI sessions if you're having some difficulty understanding this new material. But I'll see you in the next video.